three-phase circuits. So we have seen the relationships in star connected and delta connected loads. Right. So we also discussed some brief introduction to the phase sequence. Phase sequence. Okay. So we already discussed that. So depending on the phase sequence, the relationships will change. So we have this ABC phase sequence will be there. ABC or R by B phase sequence. So we have something like this ACB or RBY phase sequence. So it is usually known as positive sequence, positive phase sequence, and this is known as usually negative phase sequence. Thing is that in case of ABC phase sequence, so the relationships are VAN, VBN, and VCN. So it will be Vm sine omega t, Vm sine omega t minus 120 degrees, and this is Vm sine omega t plus 120 degrees. If you draw the phasor diagram, it will be something like this. Okay. So here you have VA.
Sir, minus 240 no, sir, that one. Omega t minus 240 for balance.
Both are same, no? We already discussed that. So Vm is sine omega t plus 120 degrees, or for your sake, write in minus plus 120 degrees. Okay, that's the best way to represent, right? So here the direction of rotation is like this. So A phase vector followed by B phase, C phase. Okay, right. So in this case, right, in this ABC case, so it will be like this. So Vm sine omega t. So this is Vm sine omega t plus 120 degrees, and this is Vm sine omega t minus 120 degrees. So how it will be? This is A phase, so this is B phase, and this will be C phase. So this is VAN, VBN, and VCN. So this is the direction of rotation. R, right? So this is AN, VBN.
The right side is for the
so this is the
negative
direction
base
of
sequence,
rotation.
right?
Yes.
So the right side is a negative base sequence, right?
Right side is
Like what? Like the right side phase diagram. What does it represent, sir?
this
Right side
one.
Okay, okay, got it.
Okay.
Yes,
No
sir.
confusion, right?
No, sir.
Okay. So if we assume that this is VAN, VBN, VCN, so this is VAN, VBN, VCN. So this is the direction of rotation. So this is VAN followed by VCN. So this is minus 120 degrees. And again, this is plus 120 degrees. Okay. So this is way to represent. Or this also can be represented in the same direction. So it will be like this in the same direction. So now it will be VBN and this is VCN. So both are same, right? Agree? So this VIN is leading by 120 degrees and this is further leading by 120 degrees. So both are correct. So in most cases, so we will represent this is VBN. So this will be VCN, and we assume that this is rotating in the counterclockwise or clockwise direction.
So the direction part I did not understand, sir. Can you repeat the directions?
So this is VAN, right? So this
Yes,
is
sir.
right, and this VBN. So VBN, if you notice that, see this is the direction. So this is leading and this is lagging, right? Agree? If this is the direction.
Yes, sir.
How much it is? 120 degrees. Likewise, this C phase. Clear?
Yes, sir.
Right. So usually this counterclockwise, so it is known as positive sequence. So most of the cases, so we use this terminology, and this is usually known as negative sequence or clockwise direction. So this is phase sequence. Clear? So depending on that, we are already seen that the line voltages, right? So they are ahead by 30 degrees or leading by 30 degrees or lagging by 30 degrees, depending on the phase sequence. So how exactly, so those relationships are, so in case of ABC phase sequence, right? ABC phase sequence. So this is the line voltages, right? This is the line voltages. So these are the phase voltages. See, with this VAB, so how you will represent VAB here?
VAN minus VBN.
V?
AN.
No, VAN minus VBN. How much it will be? Root 3 VM sine omega t. How much angle you will get here? How much you will get?
3 degrees.
How much angle that is? We already discussed that. At what angle? So it is leading.
Minus 30 degree.
Why minus 30 degree? Plus 30 degrees, right? This is the sequence. So this is plus 30 degrees. So whereas in this case, so it is VAB equal to root 3 VM sine omega t minus 30 degrees. Okay. So no confusion, right? So this is already we derived, right? So this is plus 30 degrees. This is R phase and this will be R by B. So that is plus 30 degrees here. It's clear? So in case of this phase sequence is reversed, so in this case, what is the change here? So if the phase sequence is reversed, so this is V by N, right? So instead of that, you will get V by N here, and this will be the minus V by N. So from that, so here this vector will be somewhere here. That means that is making minus 30 degrees angle. Or in other words, it is lagging. Clear? Any questions? You have any
Sir, please
questions?
explain once again, sir. Somewhat confusing it.
Why? Why you are confusing? So this is clear, right, for you?
Oh, yes, sir. That is a previous one, sir. Omega t plus 30.
This is
That is
already we studied
yes.
this, right? This is clear, right?
That one, sir. Second one,
So
sir.
if the
Second.
phase sequence is changed, if it is direction of rotation is changed, obviously, so this is the resultant. That is simple sense, right?
Okay, sir. Okay, sir.
Basis of these vectors are changed. Now it will be VBN and it will be VCN. So this is the direction it is rotating in this like this. So if you want to subtract this VAN minus VBN, so how you will follow that? So this will be the
Okay, sir.
minus
It will be yes,
VBN.
sir.
So
Minus
this will
VBN,
be
sir.
like this. It will be
Minus
like
VBN.
this, right? So now it will be this one. So how much angle it is
Lagging.
leading? How much angle
30.
it is lagging? So this is 30
Lagging
degrees.
30, sir. Lagging 30.
Okay,
Okay,
clear?
sir. Okay.
So this is in case of voltages, but in case of currents, so both will be same. Phase current, line current, so both are same, right? So this is in case of star connected. So this is in case of star connected. Similarly, in case of delta connected, if the phase sequence, so it will be you have ABC phase sequence and ACB phase sequence. Same thing, right? In case of delta connected systems, so what is the change here? Voltages will remain same, right? In delta, phase voltage and line voltage, so both are same. Only difference is the currents. Only the difference is currents, right? Phase currents you have and the line currents. So how this relationship in case of delta connection is, so if you have the line currents, so for example, this IA, IB and IC are the line currents. IA, IB and IC are the line currents. So this IA will be root 3 I phase sine omega t minus 30 degrees for positive sequence. Similarly, for negative sequence, so this IA will be √3 I phase sine omega t plus 30 degrees. Okay. Clear? So this is for voltages, but in case of currents in delta system, so this will be minus 30 degrees and this will be plus 30 degrees. Right. So why it is plus 30 degrees and minus 30 degrees? So you need to prove that. Right. So try to do that as an assignment. Understood? So take a ABC phase sequence and take ACB phase sequence in delta connected systems and prove that the line voltages and line currents relationship. One is plus 30 degrees and another one is minus 30 degrees in the same manner. So how we already done this one. So based on that, so you have to do it again. Clear? Understood?
Yes, sir.
Okay. So do that as an assignment. I will ask randomly in the next class. You got my point, right? In case of delta connected systems, so you
Sir,
need
next
to
class you have
calculate
to show sir how it got plus 30 and minus 30, sir.
yeah, in case of line currents and phase currents, so why it is plus 30? So you need to basically you need to prove the relationships plus 30 and minus 30. So I already proved this one, right? So we already discussed this in case of star. So this is the same thing you need to apply for the delta. So why exactly like that?
Sir, in delta voltage doesn't change, no, sir.
Yes, voltage doesn't change. Phase voltage
Then
and line voltage both are same.
magnitude will become same, but angles will be different.
No, angles or magnitude both are same. There is no change at all. Whatever the phase voltages are there, line voltages are the same.
Okay.
We already done this, right? So this VRY and this VR both are same only. Agree? So this is the voltage, phase voltage, right? And this is the line voltage. Both are same only, right?
Sir.
No confusion, right?
Yes, sir.
Okay. So that's where you have two phase sequences. So one is the star connect, one is the positive sequence, another one is the negative sequence. In most of the cases, we have this ABC phase sequence only. Unless to confuse you, they may give the problems on ACB phase sequence. Okay. Right. So next thing is, so let us assume that you have three-phase system is there, star connected system is there, and right. So let us assume this is three-phase. So let us assume it's 415 volts, 50 H, star connected. Right.
Is a question, sir.
Okay.
Sir,
So let us
is
assume
this a
that
question?
this is ZL and this is ZL and this is also ZL. Right. So this is what phase? It is three phase, three wire, right? Agree? This is three phase, three wire.
Yes, sir. No, there are only 3 wires.
So you have only three wires. So usually, so our power, so we have, if you study the power systems, we have two things. So one is the transmission lines and another one is the distribution lines. So usually this transmission lines is the bulk power from the generating stations is generated and it is moved to the distribution systems by using these transmission lines. So wherever we have distribution stations, so that is usually fine in our areas. Maybe you might have seen that the 11 kV by 440 volts distribution system, something like this, right? Okay, whenever your power is not there, we usually call to them. So in case of these distribution systems, so normally we have how many lines will be there? So it will be 3-phase, 4-wire. The distribution systems are usually 3-phase, 4-wire. So we have these electric poles will be there, right? So for the poles, if you observe that, so there will be 4 wires. So that means A phase, B phase, C phase, and neutral. So we have A phase, B phase, C phase, and neutral. All our poles. So from if you see that, so you will get four wires or 4 cables, right? So among there will be some top carrier will be there. Usually 5 will be there. So one is for communication or from a written path for that. So there will be some small cable will be there of that is for the purpose is different. So that maybe you will discuss in the other classes, other subject classes. So we have main 4 conductors will be there: A phase, B phase, C phase, and neutral. So this is for connecting 3-phase loads and single phase loads. 3-phase loads and single phase loads. For example, in your same vicinity, some industry is there, some small scale industry is there. So for industry, they require 3-phase. So for them, so they directly give the 3-phase supply by using A phase, B phase, C phase, and neutral. Right. For domestic application, for your home, so how they will give that? So here, A phase here and neutral. So that is how they will go. For example, this is 3-phase load. This is for some industry. So how you will connect the single phase loads? So we are using this neutral. We have A phase here, so this neutral here. So with this, the single phase loads are connected. So this is one home. So this is another home. Likewise, this is house 1, 2, house 3, house 4. If this is 415 volts, so how much voltage this is appearing here? How much voltage?
415 only, sir.
Hmm?
415 only, no, sir.
Why 415 only?
415 by root 3, sir.
415 by root 3, sir. Sorry.
3, right?
Line voltage.
415 by root 3.
Root 3, yes, sir.
So this is A phase, right? So they will. This is how they will connect. So let us assume that. So there are 3 streets in your colony. So this is street 1, right? Similarly, street 2. So we have, where is that other wire? So this is the one. So this is neutral, right? Right. This is street 2. Similarly, street 3. So it will be like this. I'm drawing only 2. You assume this is also 4. This is for 3rd street. Right. So this is how the single phase loads are connected. So this is how the single phase loads are connected. So not only they need not to use the same method. So it may be of different. Sometimes you notice that one street, say they have power, and the other street they are not. For example, this street is having no power. So what is that meaning? What is that meaning? But other street, street 2 and street 3 has power. What exactly that means?
One phase is out, sir.
There is something wrong with this A phase. Okay, maybe that fuse is blown or something. So something wrong with this A phase, right? So remember, so it is not connected to A phase, N phase. This entire street is not connected to A phase, N phase, right? So we are equally distribute them. So we need to equally distribute the loads. For example, for A phase, if you have 90 houses in your colony, so for A phase 30, B phase 30, and C phase 30. So roughly they will distribute. Okay. So roughly, so they will distribute. So for example, if you're not properly distributed, for example, this goes 50 and this goes 20 and 20. So what will happen? A phase is connected to 50 ohms and B phase 20 ohms. What will happen?
Or will be different.
So in which phase the current will be more? More load is connected to the A phase, right? So
Overloading.
obviously, so this is having more load. We assume that the loads from all means loads connected to the all homes are, for example, if same or identical. In this case, this is drawing more current. So A phase is drawing more current compared to the B phase and C phase, right? So that's why. So what
Yes,
we
sir.
had to, so what we had to do is, so we need to properly distribute these loads. If this load is not properly distributed, so what will happen? If the load is not properly distributed, what will happen? So there will be unbalanced, right? So now this load is, for example, if this is 30, 30, 30, right? So it may be balanced load, right? It may be balanced load. If something is goes, say for example, in 30 ohms, so 5 are so went for some outside, and the 5 lights or the 5 loads are not connected. Now it is running with only 25, and this is 30 and this is 30. So what it causes? It will cause some unbalance, right? Agree? So this balanced load will become an unbalanced load. This balanced load
Since they are
will
parallel
become
only, voltage will
an
be
unbalanced
same.
load.
So
Yes,
they're only parallel to the voltages, no, sir. So how?
but the currents are
So
balanced, right?
problem.
The voltages are unbalanced. Okay? The voltages are unbalanced. So let us assume that, so this we can represent unbalanced load. So let us assume this is LA and this is B and this is C. So instead of that, so all loads are same. I assume that this A phase load is ZLA, B phase is ZLB, and C phase is ZLC, and the neutral is connected here. So this current is flowing like this, and this current is flowing like this, and this is flowing like this. Right? So this neutral point and this is neutral point, right? So now where is the written path for this? So this is A phase, right? So this current is flowing like this, agree? And this B phase current is flowing like this. This is the written path, and this C phase current is flowing like this, right? So this is the, or in other words, this neutral will act as a written path for all the phases. The neutral is acting as a written path for the all the phases, right? So now tell me, right? Now tell me, if you assume this is IA, right, and this is IC, and this is IB, and this is the written current, right? So what is this value? What is this?
Plus IB plus IC.
Sir,
IA plus IB plus IC.
So it will be IA plus IB plus IC. Agree? Or if you write this, this is the direction, it will be minus of IA plus IB plus IC, right? Both are same.
yes, sir.
Okay,
Yes,
I'm
sir.
arranging to avoid confusion. So let us assume that if ZLA, ZLB, and ZLC all are equal. So in this case, so what is this value? If ZLA, if these three loads are equal, so what is the value? These three loads are equal, so what is this value? Simple question.
All currents will be same.
One simple question, if we add these three, right? If we add these three, so what is the resultant?
No, sir. Zeros.
What is the resultant?
Yes, sir.
0, right? So this is 0. So that means balanced things, so VAN, VBN, VCN, that is 0. Similarly, if it is balanced, VAB, VBC plus VCA, if we add all these three, so that is 0. Similarly, this current IA, IB, IC, if we add these three, so this is also 0, right? Agree?
Yes, sir.
Okay. So now tell me what is this value?
Zero.
If you assume that this is balanced, so this will be 0. In case of balanced load or balanced supply, so in this case, so this value is 0.
Sir, one note.
Yes.
Star connection, but the currents won't become zero, no, sir. Addition of the currents.
Hmm.
Oh, you means in delta connection that the addition of the three currents will be zero.
Whether it is star connection or an interconnection, right? Sine omega t plus phi, right? Plus sine omega t plus phi minus 120 degrees plus sine omega t plus phi minus 240 degrees. If you add all these three, you will get 0 only.
Okay, sir.
Okay.
Yes, sir.
Total current is coming in the zero when balanced supply is or balanced load.
Both. Okay, we
Both
assume that this is
cases are
balanced.
necessary or only one of them or
We assume that this is balanced. Okay, if there is unbalance in this source or unbalance in this source, so obviously this won't be 0. If there is unbalance
both
here,
should be
so
balanced.
this current won't be balanced, right? So right now we are talking about unbalance in the load. Okay, so most of the cases, so this load is balanced only. 99.9% of the cases, this load is always balanced. So right now, so we assume that this load is balanced. Okay, so this is balanced, but the source is balanced and the loads are unbalanced, right? If these are some finite values, so in this case it won't be 0, right? It won't be 0. Some current is flowing, so this current is known as neutral current. So this current is known as neutral current. So this neutral will act as a return path for the single phase loads, right? So when the loads are unbalanced, so there will be some finite amount of neutral current. There will be some finite amount of neutral current.
Since all of this will get same voltage, all will be balanced.
Hmm.
Since all
We are
houses
talking
will
about
get
the
same
currents.
voltage,
Voltages are balanced, but the currents are not balanced, right?
means as the number of houses differ, current will be okay.
So current will be different, right? Agree?
Yes, sir.
Right? Understood, right? So this is known as neutral voltage. So neutral current. So when the neutral current will exist, when the load is unbalanced, or if the source itself is unbalanced, right? If the source itself is unbalanced, even though the load is balanced or unbalanced, so this neutral current will exist. So this neutral current will exist when source is unbalanced or load is unbalanced. Most of the cases, the source will be balanced more or less, but the load will be unbalanced. Okay. So this voltage between, see here, these are the lines, right? See, these are the lines. So these lines is having some resistance and inductance. So these are basically some lines, transmission lines or distribution lines, right? From the transformer to here transformer will be there, right? So from this transformer, if your house is located somewhere here, your house is located here. So this is the transformer. So from this transformer, you have one pole here. So you have another pole here. You have another pole here. Likewise, you have another pole here. You have another pole like this, right? So from this pole, so you are getting the power. Okay. Right. So this is basically some cable, right? Or some conductor. So this conductor is having some resistance and inductance. Right. So that is known as line impedance. So this is known as line impedance. So this is known as line impedance. Right. So this line impedance so basically change with the length of the conductor. For example, your house is connected here. So in that case, only this length will be considered. Only this length will be considered, right? For example, your house is placed here. So in that case, so this entire length you need to consider from here to here. So that is known as line impedance. So this is having some resistance. So that is known as line impedance.
That means resistance per unit length, sir.
Yeah.
Resistance per unit length of the wire.
That is impedance. This entire thing will lump as a single one, not unit length. Okay. So let us assume this is 1 ohm, 1 ohm, 1 ohm, right? So this is how much ohm here? 4 ohms, right? Simple. If this is 1 ohm, so this is also 1 ohm, this is 1 ohm. So this for this house, it will 4 ohm. For this house, this is 7 ohm. Simple. Okay. This is not for the unit length. So this entire thing will lumped as a single parameter. So that is known as line impedance. Okay. So that means this how this line impedance we normally represent as. So we have this cable here. Okay. Some impedance form. Right. So this is line impedance, Z line. It may be something, maybe 0.2 plus J 0.3 ohm, something like that, some small value when compared to this load. So this is usually we assume that this is common for all. So this is having some line impedance, and so this is also having some line impedance. And this neutral is also having some line impedance. Agree? Simple. So here from the source to load, we have some conductors. Right. So this conductor is having some impedance. So that is known as line impedance. See, we normally assume that the length or the thickness or the characteristics of these conductors are more or less uniform. So that's why we assume that. So this is same. So this is also Z line and this is also Z line. Clear? So now we will define the neutral voltage. So this is transformer, right? So generally this point is usually grounded. This point is usually grounded. So that means the voltage between this VNN, right? So what is VNN? So this is load neutral and this is source neutral. Agree? So how much this
Zero,
value?
no, sir. Zero, no, sir.
This is Z line. How much this value?
IA plus IB plus IC into Z.
So this will be IA plus IB plus IC. So how it is moving? In this direction it is moving, right?
Yes, sir.
So how exactly we'll write this voltage between N and N? So we are measuring the voltage between this N and this N. How we will measure that? So IA, IB plus IC into
Z line, sir.
Z line.
Impedance.
So this is known as neutral voltage. It's clear? Or if this is, for example, this is VN and N, so how it will be? Now in this case, this N is the reference, right? It will be minus IA, IB plus IC into Z line. Is clear? Simple thing. For example, so you have one point is this is N, right? This is capital N, and this current is 10 amperes, and this is 3 ohm. So what is the neutral current here? Neutral voltage? What is the neutral voltage?
Minus 30, sir.
Minus 30. From this VNN, what is VNN?
Sir,
Plus
plus
30.
30.
Plus
Plus
30
30
degrees.
volts.
Plus 30 volts, right?
Yes,
Okay.
sir.
This is simple. Okay, this is simple.
Sir, minus, no, sir. Minus 30 should come. Sir.
That's why I'm writing here.
Small n into cap Vn small n, that is plus 30, no, sir.
Okay.
Okay.
So here this is at higher potential, right? Because the current flowing from higher potential to lower potential. So if you assume this is ground, so this voltage is 30 volts only. Clear?
Sir,
Understood? Yes?
Z line will be different for each
That's
branch,
why we are
right?
coming right. So Z line, unless specified, so it is equal for, usually it is equal for all the phases, A phase, B phase, C
Okay.
phase, and neutral also. If it is unless specified,
Okay, sir. Thank you.
unless specified, because this is basically conductor, right? So unless specified, so line voltage is basically, this voltage is basically same for all the phases. But there are certain instances, right? There are certain instances, especially when you have a computer load centers or software offices, especially. So there is some problem with the software office loads, especially its computer loads. So in that case, the neutral current will be high when compared to its phase currents. Okay. Right, this neutral current, so why it will be high? So that is not the point here. So in that case, what will happen? This is the size of the, for example, this is the diameter of the phase wires. So this is something like this. Okay. So if you assume all are same, whereas this neutral will be slightly bigger than that. Why it is bigger than that? In that case, the neutral current will be usually much higher when compared to the phase wires because of the computer loads. So computers draw some non-sinusoidal currents. Computers will draw. Now, usually we assume that the current will be like this, right? But the computer loads will not draw a current like this. So it will draw a current something like this. Okay. So why it is doing like this? That's not right now. It's not required for you. So due to that reason, the neutral current will be high when compared to this phase currents. So that's why the size will be somewhat higher to carry more current. If the size will be high, so that means it will carry more current, right? So that means neutral current length will be high, this will be high. So in that case, what will be the reason? If this winding is carrying more current, right? So this is the, in other words, the thickness will be more. We may expect that. So this Z line will, which is having more Z line, is these three will be have more, or this will have more?
Neutral wire, sir.
Hmm?
Neutral wire.
Why? If the thickness is high, so what will happen to the resistance?
Resistance will increase.
Will increase or decrease?
Decrease, sir. Royal.
Decrease.
So it will be decrease, right? Okay. So in that case, maybe the neutral wire may be, or in that case, neutral Z line for this one, or Z neutral, so it may be slightly reduced or slightly less than. So this Z line for these phases. Okay. So unless specified, all are having the same Z line or the same line impedance. If it is sometimes specified, so this neutral may be have. Sometimes we additionally connect some. Sometimes we normally what we have to do is some protection and other things. So we normally additionally connect some resistance in neutral circuits. Okay, that's not required now. So that is the thing. Okay, so this is how we will calculate the neutral current and neutral voltage. So remember, in case of delta systems, so there is no question of this neutral current. If it is connecting, if the load is connected star, if the source is also star, right? In this case, there is no question of this neutral voltage. So this is only appears. So when the load is star connected and the source is also star connected. Clear? Right. So this is an assumption that the current source current is A phase current is flowing in this direction. This load current is, or the neutral current is flowing in the opposite direction from the load to source. So in this case, it will be IA plus IB plus IC. You have any questions?
No, sir.
Sir, so in a balanced system, IA plus IB plus IC will be 0.
Yeah, exactly. In that case, if this is 0, so both VA and this is also 0, right?
Yes, sir.
So the neutral voltage is also 0.
Okay, got it,
So
sir.
that's
Thank you.
why, right? So even though this is grounded, right? So even though this is grounded, but this is having some voltage, right? So even though this point is grounded, for example, let us assume this 10 ampere current is flowing. So this is 5 ohm, right? So how much voltage it is usually here? How much voltage you will get here? If this is grounded,
Plus
so
50.
this is some plus 50 volts, right? Plus or minus that immaterial for us because it's AC. So you'll get 50 volts here, right? Agree?
Yes,
So if
sir.
you touch 50 volts, so you will get some shock, right? Okay. So that's why, so we always emphasize, so when you're constructing our house, when we are laying the cables, right. So we always emphasize, so this neutral should be grounded. So that's why we usually ground our neutrals. So when we start constructing our houses.
Other neutral also grounded, small
Hmm.
n.
Yes.
Then why didn't you show symbol?
No, what's your doubt?
Yeah,
Both
you
neutrals are.
also show the symbol of grounding,
Hmm.
small n.
No, yeah, this is to just differentiate the source. This is source neutral and this is the load neutral.
Sir, load neutral also grounded, I asking.
That's why I'm saying that's right. So sometimes we need to ground the neutral. Why we need to ground the neutral is, so this neutral is having some voltage. Okay.
In that particular cases, we
Load means the appliances we are using at house now, sir.
What? I'm not. What's your doubt?
Those impedances, load means exactly the appliances of the house or.
This is the appliances of the house. Okay.
Okay, sir.
This is the appliances, right? This is the equivalent, maybe your LED lights, TVs, and other heaters, air conditionings, all those things. So this is entire thing lumped as a ZLA. This is clear, right? So why we need to ground, right? Especially when it is computer related loads or something like that. If you touch the, sometimes if you touch the CPU, you may feel some ground, you may feel some shock. Especially this is usually common in case of refrigerators or in case of microwave ovens and other, especially in case of heatings, heaters, room heaters. Sometimes you may feel some small electric shock. So this is because of this neutral voltage. If you properly ground, right? If you properly ground at our mains terminals, so this can be avoided. Okay, so this can be avoided.
Why did you write below line impedance unbalance or load unbalance? What was you explain here?
Hmm.
What was you explain here? Line impedance below written unbalance or load unbalance. What
This
was
one.
Yes, yes, sir. What was you explained here?
No, I'm not getting your question.
What was you explained here? Why are you writing this below line impedance unbalance or load
Then
unbalance?
you're not listening the class then.
I listen, but
Then why you're asking this? You need to be focused, right? If I said something and I written something, if you're asking that why you are written this, so how can I
so
explain?
I know you explained, but I even didn't get. Means
Maybe I think maybe there are two ways for the presence of this neutral. I think maybe there are two unbalance. Okay, maybe for I think this is different and this is different. Okay, so this is to, I'm showing that this is line impedance. So this unbalance or unbalance. So this unbalance will occur maybe of two reasons, maybe because of unbalance in the source or unbalance in the load or both. So that may cause the unbalanced supply or unbalanced system. So in that case only this neutral current will exist. If the source itself is unbalanced, neutral current will exist. If the load itself is unbalanced, neutral current will exist. If both are unbalanced, so obviously this neutral current will exist. I think maybe that point I'm emphasizing here. This thing you are talking about, right?
That I know. Why you introduce line impedance? That I am talking.
This is we discussed here, right? See here, from this is the discussion about the line impedance.
Okay, sir. Okay.
You go through video once, okay, after uploading that. You're not following, it seems like. This entire discussion is for the line impedance. Okay. So any questions here?
No, sir.
So this is how the single phase power can be obtained from a three-phase supply. From three-phase supply, this is how single phase power will be obtained. So as we already discussed, for the large for industries, so usually they require three-phase supply. Right. For industry also they have other lighting loads will be there, right? So lighting loads, so those will be always, we need to connect always to the single phase. So that means for the single phase loads, so that is connected between the neutral and the phases, right? So when you are when you are giving the power to the individual houses, so we have make sure that, right, we make sure that, so we need to balance the loads. We need to balance the load. For A phase, some of the houses will go to A phase, some of the houses will go to B phase, and some of the houses will go to C phase, right? So practically, right? So practically, we cannot completely balance that, right? So we never know at what, in which house what are the different appliances are there, how much load they are consuming, right? So practically, we cannot make this neutral current zero, but somehow we can limit this neutral current, or somehow we can reduce this neutral current by properly by properly connecting the or properly distributing the loads. Right, we'll stop here. In next class, we'll discuss about the. So far, we discussed that the source is star connected and the load is also star connected. Right. Similarly, if there are other chances will be there, if the source is star connected, right, the load may be star connected or it may be delta connected. If the load is source is delta connected, it may be star connected or delta connected. Right. So far, we have seen this one. We also see in this one, right? So there are other two possibilities are there. So how this voltage current relationships will vary, so that we will discuss in the next class. And also, so how to calculate this or how to solve this unbalanced system or unbalanced three-phase supply. So we'll solve some problems in the next class. Okay. So I'm closing here.